Live streaming is on.
So, hello and welcome to the Hyderabad Women in Machine Learning and Data Science's latest meetup. And I'm really, really excited about this because we have a very special personality here this time amongst us. She's Siddha, and Siddha is such a multi-talented personality, and it'll be fun to actually get to know her and just to ask her how she does so many, how does she multitask and how has she got so many feathers in her cap. So very briefly, I'll just introduce her and then we'll just go off to her. So Siddha is an AI researcher. She's also Forbes 30 under 30. She's a self-driving architect at NVIDIA, and she's an AI advisor to NASA FDL. That's something that I'm going to ask her. And interestingly, she helped build an automated meteor detection pipeline for the NASA. So that's pretty cool. Apart from this, she has been in the computer vision field. Before NVIDIA, she was with Deep Vision, where she's done some commendable work. And she's also an advocate for diversity and inclusion technology. So you'll really find her giving talks and helping people to get into the field of deep learning and computer vision, and which exactly she's going to do with us today. And I think she's put all her knowledge, and the best part is she's shared her knowledge with others through a wonderfully written book that she's co-authored with two other people. And the book is called Practical Deep Learning for Cloud, Mobile, and Edge. Excellent book. I have read it. It's super lucid, super simple to understand. And we'll go more into it, and we'll talk to Siddha about her journey into AI, her inspiration for writing the book, and any questions that you have for her. So over to you, Siddha. Welcome, and thank you so much for being available. And it's pretty early there at your time, so we're really thankful, and we're really, really so excited to talk to you.
Thank you for having me. I'm really excited to be here.
So before you start with your presentation, we would just like to know, how did you get into the space? What motivated you? What inspired you? And then your journey with NASA.
Sure. So I got started in computer science during my school mostly. We had a really nice computer science course back in, I think, 9th and 10th grade. And, that really introduced me to what computer science really is and what programming really is. And then I eventually decided to, take up computer science later on in my bachelor degree at NIT Hamirpur. And of course, back then, we didn't have a full-fledged field that AI is today. So I would go on experimenting with different fields of computer science, right? Mobile application development, networking, databases, right? And then I finally found machine learning through the online MOOCs that I just started in 2012. And, there was this really famous course of machine learning by Andrew Ang. So I decided to take it. And I think a lot of people, that's really the starting point of, getting into machine learning. And so I also took that. And, initially, of course, it was relatively hard. I don't think I understood anything, but I kept at it. And I also started looking at different courses that were online. So I remember on YouTube, there was another course from Caltech on machine learning. And how professors, they teach machine learning very differently, right? Depending on who the audience is. And that really opened, a lot of new doors for me. And so I started getting interested in machine learning. I started building some small projects. And eventually during my bachelor's, both of my major projects were centered around deep learning and how we can use it for audio recognition. And so I started building some small projects. And then I graduated from NIT Hamirpur. I did a short internship at CERN, where I again used, some of the data analytics techniques on their the Large Hadron Collider data. And then I started my graduation at CMU, at Carnegie Mellon University. And again, I worked a lot on deep learning, specifically for computer vision. And yeah, that's how I really got started. And then, I joined the industry. I worked for a startup for some time. And, as startups usually are, you learn a huge amount there. And so I had a great experience at the startup, and then a few years ago, I joined NVIDIA, and I'm working on their self-driving team right now.
Awesome, awesome. It's a great to know about your journey, and I'm sure our participants and the people who are currently watching it live would also be benefited. So yeah, over to you, Siddharth.
Thank you. I'll just start sharing my screen. Okay, can you see my screen?
Yes.
All right. So before I begin, I really want to say a huge thank you to Parul and all the other organizers. It takes a huge amount of effort, a huge amount of time to bring together a successful meetup, especially in the unprecedented times that we're living in. So huge thank you. Now, today I want to talk about the 30 golden rules of deep learning performance, but let's try to figure out why these 30 golden rules are important and where are they really coming from. So, there's a saying on the internet that if you want to be good at something, put 10,000 hours of effort into it, right? But cumulatively, that's a little more than a year. So if you want to do everything, right? If you want to buy a bulb or if you want to buy a new computer, you're going to have to put in a year worth of effort trying to figure out what is the temperature of the bulb you want. Do you want a bulb that shines with a yellowish tinge or with a cool white light, right? So everything takes a lot of time. Now, there are two ways to really, figuring out which bulb to buy as an example. You can either become a self-taught expert, so you can read all the blogs out there, all the articles, and figure out which bulb is suitable for your needs, or you can take kind of the Tesla way, right? The Nikola Tesla way. You can actually go out and figure, okay, this material is really nice for a bulb, so I'm going to build a bulb with that, right? And most of us, I think, prefer the first way. So we want to stand on the shoulders of giants. We want to relearn or reuse things that are already out there. And that's really how these rules of deep learning performance have been developed. Now, a lot of it is stuff that my co-authors and I have learned throughout our journey worth of 2 decades. And a lot of these techniques are stuff that existed before us, stuff that we've learned when we failed on some things. And it's really a lot of our experience condensed into making some things as performant as possible. And of course, today I'm just going to be giving a 1 hour worth of experience, but the knowledge that we present cumulatively is also present in the book that we co-authored, and a lot of the components are available in much more depth and much more breadth in the book itself. Now, before I get into the meat of the book, of the presentation, I also want to mention a small motivation. Now, the last chapter of the book is on AWS Deep Racer and how you can get started deploying a virtual car in a virtual environment. And as a slight nudge to our readers, we mentioned that the next level is the RoboRace Championship. And RoboRace is basically you take Formula One racing and you make it autonomous, you get RoboRace. So it's an AI-enabled car at 200 miles per hour. And a couple months later, the group of students from Carnegie Mellon University is actually joining the RoboRace competition, and they'll be competing in the next upcoming iteration. And this is a student-led team. So it's not, there are, of course, professors involved, but it's really a student initiative. And that's why it's really amazing to see the amount of motivation and drive that students have everywhere. And now, before I go any further, let's make sure that everybody's on the same page. So we'll talk about transfer learning, which is approximately 95% of all training in the industry AI problems. So transfer learning is basically the technique of modifying a pre-trained network to work on another task. So if we have an example, let's say I already know how to play a musical instrument, but let's say I also want to learn something new. So I want to learn the melodica. Now, if I'm starting from scratch, this effort may take, give or take, 3 months. But if I already know how to play the piano, right, I'm reducing the effort and the time to approximately 3 days. And the reason behind this is I probably already have the knowledge of music, the theory of music, and all I really need to do is practice the breathing technique while playing the keys. So in terms of deep learning, we know that in a neural network architecture, usually the generic knowledge layers are towards the input section or the beginning section of a network. And the output layers are usually task specific, and these are towards the top or the head of the network. And in terms of fine tuning or transfer learning, we are basically clipping out the last few layers that are task specific, and we are replacing new layers. So let's say task Y specific layers, and we're also doing some rounds of training. So training while doing fine tuning or transfer learning to make sure that the input layers or the layers in green are fully compatible with the task Y layers. Now, if you want to try out transfer learning or fine tuning in 30 lines of code just in your browser itself, you can go to this link at the bottom of the slide and just press the Colab button to run a whole notebook of transfer learning on Google Colab. Now, in terms of hardware availability, right? I think this is a question that a lot of us have asked. I don't have a lot of GPUs at hand. Can I still do machine learning or deep learning? And the answer is yes. And in life, we know that what we want is not necessarily what we can afford. And so throughout this conversation today or the discussion today, we're going to see how to make maximum use of the hardware that you have at hand. So whatever hardware, CPU, GPU, TPU you have available, we're going to talk about some techniques that can make it as performant and as efficient as possible. And that's really where the 30 golden rules fit in. So let's take a look at what exactly is the culprit of slowness, or what exactly is that we want to optimize. So when we look at the process flow, we see that it's often the CPU traditionally that is doing data preparation, any data pre-processing or processing. And then once the CPU cycle finishes, the data is passed to the GPU or the TPU or any higher compute available that starts the training process. Now, during this time, the CPU is idle, as was the GPU before. Now, this cycle of idleness actually continues on and on. And this is exactly the time that starves the GPU because it's really just empty and doing nothing. And so this is exactly what we want to optimize. And throughout the session, we will talk about some tips and tricks that will reduce the GPU and the CPU starvation. Now, how do we measure the starvation of a GPU or a CPU? How do we measure that the GPU or the CPU is not actually doing anything during the time or during some particular times that a program is running? And this calls for profilers. So there are a bunch of profilers out there, but I'll focus on two today. One is a very visual approach with TensorFlow profiler, and you can enable it into TensorBoard as well. And this is a very visual approach. It can run in your browser. And like most profilers, it offers a millisecond approach. So here we can see from the 0 millisecond to the 120 millisecond mark, the GPU timeline is absolutely empty. So that indicates that the GPU is being starved during this time. And enabling TensorFlow profiler is also easy. It's a couple of lines added to the TensorBoard callback command. But of course, setting up TensorFlow profiler, and in fact, setting up any profiler does take some amount of time. And maybe for profiling, we don't really need as much information out there, because what we're really looking at is the GPU utilization number. So we can also use a very simple command known as the NVIDIA SMI, or the NVIDIA System Management Interface. And this gives us a bunch of metrics, but the most important one that we want to see right now is the GPU utilization number. So here we see that it's 51%. And what it really means is that throughout the progression of whatever program that we were running, we are effectively making use of only 49% or 51% of the GPU. So 49% of our investment is really not being used. And this is exactly what we want to boost to 99 or 100%. And of course, we want to be profiling or running NVIDIA SMI commands throughout the duration of a program. So we can also run it with the watch command. So a simple watch minus -n.5, which will run the NVIDIA SMI command every half a second. So a quick summary so far, we know what to optimize. We want to optimize GPU starvation. We have a success metric, which is the utilization or empty timelines that we want to fill up. And we will be viewing our results through profilers. And again, we will be looking at the 30 rules that are passed over preparation, data reading, augmentation, training, and inference that will slowly improve our pipeline into an extremely performant and efficient pipeline. So in terms of data preparation, there are a couple of anti-patterns out there. The most common one, especially in data sets, is that we have millions and millions of thousands of tiny files, but they are often stored as one gigantic multi-gigabyte file. Now, the issue here is that because the individual files are really small, there is a lot of overhead in seeking those files. And ultimately, the gigantic multi-gigabyte file that we have, because it's so big, it reduces the ability to make parallel reads and parallel network calls. Now, this slowdown is even more extreme when you imagine reading files over a network. And of course, there are other factors like latency that come into play here as well. Now, the solution is to store the data as a TF record file, which is a very common format in TensorFlow. And the underlying serialization format in TensorFlow is usually the protocol buffer format, which stores the model in the same format as well as the data files. So the idea is to store these individual small files into one TF record file about the size of 100 megabytes. So you can have multiple 100 megabyte files from the individual, let's say, ImageNet dataset or any dataset that you have. And this 100 megabyte file is considered the sweet spot because based on a lot of experiments, 100 megabyte file is usually good for parallel reads and parallel network calls as well. So that was our first rule, storing as TensorFlow record datasets. Next is, of course, reducing the size of the input data, right? Because every time we train, we pre-process, we read the data from disk, we pre-process, and that in itself is a lot of repetition. So the good idea here is to store the pre-processed data as a TF record dataset. So whatever pre-processing it be, resizing, cropping, all you have to do is store it in a TF record format and then read that TF record format in and train and then keep iterating on the problem as such. And then, of course, we are talking about TF records, so why not use the TensorFlow datasets that are already provided? Now, TensorFlow datasets or TFDS provides more than 200 datasets to download. And this is, of course, opposed to the fact that we usually download the raw, unprocessed, non-TF record data. And so obviously using the TF record data is a much simpler and a much easier task. And it offers a lot of vision, language, audio, and even the CH expert dataset is based on the chest X-ray dataset that is extremely relevant for COVID-19 research, if that's the direction of your research. So there are a lot of datasets coming up, and it's also relatively easy to add new dataset using the TF record format to an existing pipeline of TF TensorFlow datasets. And of course, using TensorFlow datasets is also relatively easy. It's a few lines of code, and
Siddha? Siddha, can you hear us? I think we've just lost Siddha, so we'll just try reconnecting with her again.
line.
Siddha, you're back?
Can you hear me?
Yeah, we just lost you actually.
Oh, all right. What was the last slide that?
So we are watching the pro tip. So we lost you.
All right, let me go back. Okay, so here, okay, so I just stopped talking about data.
You need to reshare your screen too. You need to reshare
Oh,
your
okay,
screen.
okay. All right. Let me see.
Yeah, we're back.
Okay, perfect. And you can see my presentation as well, right?
Yes, everything's fine now.
All right, okay. So before I was mentioning a pro tip, which is to publish your dataset in your line of research on TensorFlow datasets as well, because it's relatively easier for others to build on this work. Next, we're going to talk about data reading, because now our dataset is prepped up and we're going to try to improve the throughput of the data reading pipeline itself. Now, of course, because we're looking at the TensorFlow data pipeline or the TF data pipeline, the basic pipeline will look something like this, right? So we are shuffling the data, we're repeating it in batches, we're going to break it into a batch size, and we're going to parse the labels of it as well. Now, In the next couple of slides, we're going to have one optimization per slide where, eventually we will build up to an approximately 10% improvement in performance. And so the first one here is prefetching data. And the problem or the bad idea that we're trying to solve here is that there is a circular dependency between the CPU and the GPU. So the GPU is going to wait for the CPU to produce the data. It's going to be idle during this time. And once the GPU has finished processing or is processing, the CPU is idle during that time. So one way to solve this is to delink the production of the data from the CPU by the consumption of the data, which is by the GPU. So we're going to have a buffer in place to which the CPU continuously sends data whenever it's pre-processed it. And the GPU is directly going to read from this buffer. Now, this is going to be happening asynchronously. So the CPU or the GPU don't have to wait for each other. And it reduces the idle time for both by a lot. And so working with the prefetch option in TensorFlow is relatively easy. We have to define a buffer size. Now, the only constraint to keep in mind is that this buffer size should be big enough to fill in the entire next batch of data that the GPU is going to intake. Then we also want to parallelize the CPU processing. So we've previously looked into parallelizing CPU processing, and it's best to parallelize according to the number of CPU cores that are available. Otherwise, we'll have too much context switching, and there are a bunch of command line options to try out to figure out how many cores are available and how do you program the code to make sure that it takes advantage of processing options.
Sada, I don't know if the participants, they cannot see the screen, the slides. Could you?
Okay. All right, let me see. Let me try to share again.
Even though I can see on the...
Are you still streaming on YouTube?
Yeah, it is on YouTube.
Okay.
So people can hear your voice, but they cannot seem to see the slide.
Is it visible now?
So I think it is visible perfectly. Let me just confirm with the participants that they can see.
Sure.
I think... Okay, now it's perfect. I know why that is.
Do you want me to go back?
No, I think they could hear you, but they just couldn't see your slides.
Okay. All right. So let me continue from here onwards.
Sure.
So the next rule is to try to parallelize the I/O and subsequent processing. And this is usually called interleaving. And the idea here is that we want to abstract away the reading of the data from the processing of the data. Because as we looked at earlier, reading files from disk or even on a network is a huge cause of bottlenecks. And that requires us to optimize our file reads. And one way to do that is to parallelize the reading of the file versus the processing of the file. So we don't want to be processing the file that has just been read. Instead, we can have a buffer where we are reading the files and parallelizing their processing later on. And of course, for us, it means we are parallelizing the extraction of the TF record format files that we had developed earlier. Now, another really important thing to consider while reading data is that when we read data, we usually read it in a sequential order, right? We'll read image 1, image 2, image 3, and so on. But in our training pipelines, we also have a randomization option or a shuffle option to make sure that our network or our trained model does not learn any implicit order in the dataset itself or in the ordering of the dataset itself. So rather than reading sequentially and then randomizing or shuffling the data, why don't we just read in a non-deterministic order? And of course, this has another hidden advantage. And the advantage is that if there is a really slow, single slow operation, that often holds up the rest of the pipeline. So this straggler or the single slow operation reduces the performance of the entire pipeline. Now, most data reading pipelines operate in a fixed round robin order, and this straggler or the single slow operation can be a huge loss in performance. So we can enable non-deterministic ordering and have all the operations of the reading done out of order. And of course, like most shuffling or randomization operations, it's necessary to set a random seed, both in TensorFlow, NumPy, or wherever you're reading the files, or even in Python, because it makes the experiment set more reproducible and traceable. And that helps a lot in moving towards the explainability portion of TensorFlow or the program itself. Now, another interesting thing to look at is to cache the data as much as possible. And TensorFlow allows caching both in memory as well as on disk, depending on how much you want to cache and how much buffer size is actually available to TensorFlow. And in this case, we of course want to cache the TensorFlow record files that we had saved earlier to disk, and the caching will really help us when we are reading the files for training. Now, most frameworks are usually community-led, and there are always optimizations and developments that are available higher up in the branch, or usually in the development branches, but they're not yet released. So it's worth looking into if something relevant has popped up. And an easy way to do it is to turn on the experimental optimizations through the options available. And a lot of times, these offer improvement in speed up and just making the pipeline more and more performant. Now, a very common issue that grapples beginners and people who are just starting out in this industry is, what should be the initial value for my parameters? I have learning rate, buffer size, how many threads, how do we figure out all these values? And so the best solution really is to auto-tune it and forget about all the worries. And so auto-tuning is another one of the experimental options that have been recently made available. And, in this example, we are auto-tuning the buffer size for the prefetch that we saw earlier. So similarly, you can auto-tune as many parameter values as you want. And the good thing here is that because you're auto-tuning the buffer size, and the buffer size is often related to the underlying hardware you have, TensorFlow in a way is optimizing your network and your pipeline for the particular hardware. Now, combining it all into a single pipeline, adding caching, adding interleaving, still develops a much more enhanced pipeline. And all of this code is really going to make the program wildly faster. Moving on to data augmentation. Data pre-processing and augmentation techniques are super, super elaborate, but at the end of the day, they are often based on matrix operations. So translation is a matrix operation. Augmentation, adding noise is often a matrix operation. And given that all of these are matrix operations, they work really well on GPUs. The downside is that most of the libraries like OpenCV, Pillow, or even the built-in augmentation function in Keras, they don't necessarily utilize the GPU for pre-processing or augmentation. Of course, with OpenCV, you can build it to use the underlying CUDA pipelines, but by default, it just isn't available. So one good option is to try to use the GPU for different augmentation techniques. And currently, there are two methods of doing that. One is with TF image, so TensorFlow's image pipeline. Now, of course, this is, again, a community-led effort, so it's not as developed as other frameworks out there. For example, you can only rotate an image by 90 degrees. You cannot rotate it by a random amount of degrees. So it has limited functionality. But again, the bright side here is that both Keras and TensorFlow have enough GitHub tickets out there that if you're willing to contribute to it and just write the code for it, it is still possible to do it. Now, another option that is slightly more prevalent is this library known as DALI, and it's released by NVIDIA, and it works with a lot of the deep learning frameworks out there, so PyTorch, TensorFlow, Caffe, and so on, and it internally leverages the GPU for all augmentation techniques. So be it decoding, so if you have a video file, image file, it can encode, decode, it can resize, augment, and so many other operations are available that are GPU enhanced within DALI. Now, another advantage of using DALI is that it's already being used by most of the teams and the competitors to break industry benchmarks. So later on, we're going to look at some of the benchmarks like MLPerf and DawnBench. And a lot of those teams are always using DALI to improve their speed and performance for GPU augmentation, of course. Now, moving on to the training section, I just want to check, Carol, you can still see and hear the slides in my screen?
Yes, it's perfect.
Okay, perfect. All right. So the training portion, one of the most common ways to make your training 2 to 3 times faster is to use mixed precision. And mixed precision really means that, let's say you are in a 32-bit training format, or your program is in 32-bit. And so if you go from 32-bit to 16-bit, you're effectively doubling, absolutely everything else. You're effectively doubling the memory bandwidth available, or the batch size that can be accommodated, or the model size that can be trained. And not only that, but it also improves the speed at which computation happens. And usually for inference, with mixed precision, you can convert your model to something even lower than 16-bit. So something like int 16 or int 8 is even more common. And in fact, for some of the mobile deployment, iOS devices and Core ML actually offer quantization all the way to 1 bit, which is a great amount of improvement in performance. Now, manually performing automatic mixed precision is a relatively involved task. So there are a lot of libraries out there. For example, within TensorFlow itself, you can switch the automatic mixed precision flag, or there is another library called Automatic Mixed Precision by NVIDIA. And all of they really enable automatic mixed precision to take place with minimal manual involvement. And the advantage of most of the libraries that do automatic mixed precision is really twofold. So one, when you're doing the forward pass and the backward pass, you're still getting the enhanced speed from the lower precision. And at the same time, the second advantage is that when the forward pass and the backward pass complete, the weights are actually moved to a higher precision, so a 32-bit precision, so that you're actually getting all the weights. Let's say if you have a weight that is 10 raised to a minus 6 or 10 raised to a minus 7, so that won't really register when you have a lower precision. But because you also have a copy of the model that is at a higher precision, you still have that weight registered. So it's really a lot of advantage to use automatic mixed precision. And because it's a lot of libraries do this automatically, it's a 2 to 3 times faster without without doing a lot of manual work. Now, this is a really interesting one, using larger batch size. Now, some of the more recent GPU architectures, they have a relatively big RAM. And so here we have an experiment of using the MobileNet architecture on the 2080 Ti GPU. And now that by default has a memory of 11 gigabytes. And that is actually enough for training some of the more efficient models like MobileNet. So the blue line that we see here is that even if we take a 500 image batch size, we still get about 75%. We still get a low utilization. So if you want to go higher in terms of utilization, we can definitely bring a heavier model like some of the ResNet family, ResNet 50, and so on, to improve the GPU utilization, or of course, increase the batch size as much as we want. Now, another really interesting rule that came out of a case study that NVIDIA published a couple of years ago, where they saw that when the batch size was a multiple of 8, the throughput increased by 5x, so it improved the performance by 5x. And the inherent reason behind that is most of the specialized hardware, so from the CPUs to the GPUs to the TPUs, and as we increase the specialization of the hardware, there is usually a defined size of numeric multiplication, which often has a minimum amount of requirement, and that is often divisible by 8. So a good rule of thumb is to use 64 or 256 in some of the more recent architectures of NVIDIA GPUs. And if you're using one of the TPUs from Google, a batch size of 128 is the most common and the most preferred one. Learning rate. Learning rate is really the one hyperparameter that really affects the speed of convergence. And of course, if the learning rate is too high, we will shoot past the global minima. And if the learning rate is too low, it'll take too long to actually reach the minimum point. So one way to automatically find the learning rate is from a really interesting library known as the Keras LR Finder. And this has also been implemented in the FastAI library. And the idea behind it is that you have to find the point at which we have the maximum reduction in loss. And that's really the point where at which learning rate we want to keep for the rest of the program or for the rest of the training. And so using this Keras LR Finder library, we can find the optimal learning rate, and we can perform more enhanced training versions with this learning rate that we've just found. Now, TensorFlow has actually moved from 1.0 to 2.0. And in 1.0, we had graph execution, whereas in 2.0, we have eager execution mode. And this added flexibility to go to eager execution actually comes at a very tiny cost, which is usually in the order of microseconds. But if you're doing something like a heavier training, like training ResNet 50 as an example, this can actually count to a lot of microseconds and have a sizable impact. So one of the solution is to add the @tf dot function, which makes sure that the execution is in graph mode. And so just adding this @tf dot function has an approximate 10% or 10 times speed up for each function that it does graph execution on. And of course, throughout the pipeline that we've talked about, we've covered some really small, simple steps that contributes to a huge improvement in the end. Now, another common rule of thumb in machine learning is to overtrain and generalize. Now, taking a real life example, let's say I want to learn a new language. Let's say I want to learn French. So one option I have is to find a dictionary and to learn all the words in the French vocabulary. Now, another option is to just take the 50 most common words in the French language, learn them, and then so on, sample words from the French language and add them to my vocabulary. And this is something that works really well in machine learning and deep learning as well, because we want the basic pipeline to be there, but we don't necessarily need the pipeline to learn anything or learn anything good, right? And so in terms of deep learning or machine learning, what we really want to do is this thing known as progressive sampling. So we want to read, let's say, 10 classes from the ImageNet dataset, and then train on them for a few epochs, and then add 10 more to the sampling. So do sampling on 20 classes and then train on. And then with this, the accuracy usually has a higher increase much quicker. And of course, it's also easier to debug. Now, another overtraining and then generalizing strategy is progressive augmentation. So we want to add augmentations one by one. We want to see how the impact of each augmentation that we're adding to the pipeline. And finally, progressive resizing. Progressive resizing was also made really famous by the Fast AI course. And the idea here is that you start from a smaller image size and you effectively increase the image size as you go on in your training strategy. So let's say initially we are starting with a 16 times smaller image, and that'll of course increase the rate at which we can train and prototype, because it'll give us much more higher speed up. And an interesting thing that was noted in one of the case studies or one of the papers published by the Fast AI community was that when the images are of a smaller resolution, the network usually learns high level details like colors of different objects or shapes. So what does a cup look like versus what does a plate look like? And then when higher resolution images were fed, it was often seen that the network was learning much more fine-grained details. And this is very common even when we do a face recognition or a face or anything that's trained on faces. So initially it learns, that eyes are usually above the nose and that the mouth is below the nose. But when we add more higher resolution images, we often see that, it can distinctively learn the difference between, let's say, my face and someone else's face. And so that is progressive resizing, and it's a really common technique to use while training a network. Now, another idea is to install an optimized stack for the hardware. And I honestly cannot stress on this enough. And what you really want to do is make sure that the software stack that you are using on top of whatever hardware is available is really efficient and based on that hardware itself. if you look at any of the hosted binaries for any open source package, they are expected to run on a variety of hardware and software configurations. So they're going to support, let's say, a laptop or a desktop that just came out recently, as well as a laptop or desktop that came out 5 or 6 years ago. Now, in terms of hardware improvement, there's obviously a lot of hardware improvement that is going to be available in the current laptop, right? But the open source binaries are broad spectrum enough that they have to cater to all. But at the same time, it doesn't mean that it's effectively making use of all the hardware acceleration available in your hardware. So one easy way to do it is, if you're using TensorFlow, perform a basal build of the TensorFlow. And of course, this will take some time. So the other option is to use the Anaconda pipeline. It's relatively shorter in terms of the time it takes, and it installs the Intel math kernel library. Another option is to use containers that are GPU optimized. So NVIDIA publishes these containers on the NGC website or NVIDIA GPU Cloud website, where there are a bunch of containers, different models that are optimized for a particular hardware stack. So really easy to use and offers so much more acceleration just based on the hardware stack. All right, so building on what we learned on before, we also want to optimize the number of parallel CPU threads while training. So exploit parallelism between CPU threads. And this is based on the number of CPU threads that are on a per operation level. So we want to optimize both for a per operation level or an intra-operation as well as inter-operation level. And both of them have slightly different commands, the inter-operation parallelism and the intra-operational parallelism. So the next one, and I'm slowly coming towards the end of the presentation as well. So the next one is to, of course, use a better hardware. And if you just look at the improvement in hardware for the past couple of years, so the V100 GPUs came out a couple of years ago, and a combination of these 16 V100 GPUs gave a performance of 2 petaflops. And one of the more recent architectures, the A100 chip that was released in March of this year, offers 5 petaflops. So it's just, one single chip offers so much more improvement in terms of performance and throughput. And so using better hardware is really, a one-stop shop for improvement in training time. And if you do have multiple GPUs, it's also ideal to distribute the training. And the scaling strategy for distribution really depends on what is the hardware architecture or how the distribution is of the hardware. So if you have a single node multi-GPU or multi-node multi-GPU kind of use case, you want to apply different kind of strategies to it. And another thing to note is that in terms of distribution, some networks do really well. Like in classification, distribution doesn't affect the performance at all. But in detection or segmentation examples, it's really important to make sure that all the classes of that are being detected are seen in each batch, in each GPU. So that takes some amount of code, but a lot of it is already available within the TensorFlow dataset pipelines. And apart from the TensorFlow dataset pipeline, there's also the Horowitz framework, which was released by Uber. And this is also, again, very commonly used to distribute training for any task. Now, I do want to check how much time we have before I move forward.
Yes, you can move. We have time.
Okay, all right. So taking a look at industry benchmarks like the Dawn Bench or the MLPerf, that really shows us that we don't need expensive GPUs to train or to buy and really train our networks on them. And some of the benchmarks have a really interesting premise. For example, this particular example of the Dawn Bench benchmark actually shows that there's a team known as the Apsara AI Acceleration Team who's been training within the Alibaba Cloud Network. And it takes them $7.43 to train ImageNet to approximately 93% accuracy. And that is a pretty nice benchmark. And again, the time to accuracy is approximately 3 minutes. And this is really interesting because it shows that with the right amount of augmentation, with the right amount of training strategy, you don't actually need months and months of training to get to 93% accuracy on any data set, even as as involved as the ImageNet data set is. And another benchmark more on the hardware performance side of things is the MLPerf benchmark. And most benchmarks usually have the task of training ImageNet for either classification, detection, and so on. So looking at these examples, we see Google is successfully able to train ImageNet in 1.23 to 8 minutes. And when we look at the number of accelerators, they're actually using a huge amount of TPUs. And I don't know, the cost for this is probably above maybe 100,000 or maybe more than $300,000. So it's, we have benchmarks on both sides, how cheaply we can train and how quickly we can train, pushing the maximum amount of hardware available. And a lot of the cloud companies today, Amazon, Microsoft, Google, all of them offer a lot of these amazing architectures of GPUs, CPUs, TPUs. And of course, most of the top 5 supercomputers that are available out there are actually rentable in the cloud. And if you have a student account, you can also get a lot of credits from all these cloud companies to use and experiment with a student account. Now on to the last section, which is inference. So we're going to see how to do some improvements with the inference pipelines. Now, it's a really common thing to consider that while deployment, we need the network or the model to really run as fast as possible, versus in the research side, we often look at what is the biggest model out there, how many parameters can I increase up to, how can I train on 1,000 machines at once? And so on the deployment side, we usually want to ask the question, does your 500 megabyte model spark joy? If it doesn't, just discard it. And often that means using an efficient and accurate model, which is usually in the ResNet 18 MobileNet area. And of course, the most efficient model changes from your classification task, detection, segmentation to a language model. So in terms of classification, it's usually the MobileNet V2 or the NASNet mobile, which is considered. In terms of detection, it's usually the efficient detect model that is, or efficient det model that is usually used. And in terms of NLP, there's again this huge challenge of how many parameters can we put into a model and how big can we make the model. But of course, for deployment, that's not really feasible. So the Distil-BERT model is usually the one that is most commonly used for NLP-based deployments. Now, for deployment, quantization is also a very common technique to reduce the size of the final model. And the idea is, of course, you go from a 32-bit model to an 8-bit model, you're reducing the corresponding model size. But the most important bit in quantization is actually how you are quantizing, or the underlying algorithm that you're using for quantizing the model. So we did some experiments with deploying on iOS devices with TensorFlow models. And so we looked at 3 different algorithms that are provided by default in CoreML, which is the Apple framework to deploy on iOS devices. And we saw that the size decrease is approximately 75% to go from 32-bit to 8-bit, but the percentage match with the 32-bit result is actually still at 98%. So depending